Have you ever wondered how BIM and structural analysis merge to change bridge design? I'm Jan Ostersch, the product owner of ALLPLAN Bridge, and today we'll explore how this integration paves the way for more innovative and sustainable infrastructure solutions. As we've explored in our previous presentations, our project success hinges on several critical factors. We've delved into the challenges of starting with incomplete data, adapting to project additions and changes, navigating process insecurity, and managing the overload of project handling. We've also highlighted the importance of creating further models and facilitating effective communication between experts. Our strategy to address these challenges emphasizes flexibility, precision, reusability, and both manual and automatic optimization within parametric modeling. These elements are crucial for improving efficiency and ensuring our project success. Here, I want to focus on a pivotal aspect that underpins all these strategies, establishing a single source of truth. While we've touched upon various components that contribute to our project's efficiency, the concept of a single source of truth is what truly ensures the coherence and reliability of our efforts. Why is a single source of truth so critical? In the complex ecosystem of our project, data is constantly evolving, from initial design parameters to final output. The integrity of our data directly impacts every decision we make. Without a centralized, authoritative data repository, we risk basing our decisions on conflicting, outdated, or inaccurate information. This not only compromises the precision of our work, but can lead to costly delays and errors. By establishing a single source of truth, we achieve several key benefits. Data consistency, ensuring that everyone involved in the project is working with the same most up-to-date information. Accuracy, reducing errors by eliminating discrepancies between different data sources. Integrity, maintaining the quality and reliability of our data throughout the project lifecycle, and efficient decision-making, streamlining processes by providing a clear, reliable basis for every decision. This approach not only enhances our project's efficiency, but also builds a foundation of trust and reliability in our work. Just as ALLPLAN Bridge serves as a collaborative platform for two fundamental roles in a project, the structural engineer and the modeler, by sharing a unified geometrical and analytical model. The concept of a single source of truth harmonizes our approach to managing project data and workflows. In this shared environment, while the structural engineer conducts analysis and design checks, the modeler, or the detailer, on the other hand, refines the geometrical model for analysis and crafts all necessary geometrical features. This seamless integration ensures that both parties are not just working with the same data, but that this data remains consistent, accurate, and up-to-date throughout the project lifecycle. Now let's take a look at the modeling approaches our platform supports and the current state of analysis for each. First up is axis-based modeling. This method involves creating geometry by extruding along an axis, with the flexibility to vary designs as needed. We fully support analysis for this approach, ensuring that designs are not only flexible, but also structurally sound. Next, we have polygonal modeling. This approach is particularly useful when the design of the superstructure is influenced by the substructure, or when modeling precast elements. It allows for an integrated design and analysis process, ensuring that all aspects of the structure are considered and analyzed together. Lastly, we introduce free parametric modeling, which uses 3D bodies for creating complex structures like culverts or abutments. While this approach offers significant design flexibility, it's important to note that we are still developing the analysis capabilities for these models, and this is a key area of focus for us. In our exploration of modeling approaches, it's crucial we also highlight the advanced solutions we offer for modeling tendons, a key component in many of our projects. Tendons, with their unique requirements, benefit from a range of sophisticated modeling techniques available in our system. Firstly, Tendons can be precisely modeled using points as constraints, allowing for exact placement and alignment within the structural model. For more dynamic and flexible modeling, tendons can be variated through tables, utilizing parametric points. This method offers the adaptability needed to model tendons in complex geometries accurately. Moreover, the definition of tendons isn't limited to just points and variations. We also incorporate the use of tangents and radii, providing an additional layer of precision and control in the modeling process. Beyond these core methods, our system is equipped with additional features designed to enhance the tendon modeling process. Developed views offer a comprehensive perspective of the tendon's placement and path. Intelligent tools for copying, moving, and mirroring simplify the process of adjusting tendon layouts across the model. The quick assignment feature for straight ends and beginnings, along with the ability to define additional boundary conditions, further streamlines the modeling process. Each of these features is designed with the user in mind, ensuring that the complex task of tendon modeling is as efficient and accurate as possible. By leveraging these sophisticated modeling solutions, users can achieve a higher level of detail and precision in their projects, ultimately leading to better performing and more reliable structures. In this slide, we'll look into the critical role of information in building information modeling for infrastructure projects, particularly focusing on the integration and attribution compliant with IFC 4.3 standards in bridge projects. The journey begins as soon as we initiate a new project, where the IFC bridge type is established at the project level, setting a standard that applies across the project. This foundational step ensures that every component of the project aligns with the specified IFC classification, fostering consistency and interoperability from the outset. Moving deeper into the project structure, the IFC type becomes more specific at the cross-section level. For example, an element might be classified as an IFC beam, to which we assign a custom name, such as main girder, to precisely describe its role within the project. This level of detail enhances the clarity and specificity of the project's BIM data, facilitating more accurate analysis and collaboration. The next layer of detail involves defining the IFC category for specific bridge parts, like the IFC bridge part superstructure. This categorization further refines the project's data structure, enabling detailed tracking and management of each component. This structured data is then seamlessly integrated into ALLPLAN engineering, where it serves as the foundation for further detailing. Here, additional predefined or custom attributes can be added, enriching the project's BIM data with even more depth and flexibility. This process not only ensures compliance with IFC 4.3 standards, but also enhances the project's interoperability and the effectiveness of collaboration across different platforms and teams. Let's take a look now at how we bridge the gap between our geometrical models and their analytical counterparts. The journey from geometry to analysis is streamlined, leveraging the detailed work already accomplished by the modeler. At the core of this transition is the utilization of the geometrical model's defined data. The structural engineer enriches this foundation by adding essential elements such as material properties and structural connection. The beauty of this approach is that the bulk of the necessary data resides within the geometrical model itself. Our system then takes control, analyzing the geometry to automatically generate the required data for crafting an analytical model. This includes the intelligent numbering of elements, which can be executed automatically or tailored by the user to fit specific needs. Following this, our software skillfully creates the analytical model, establishing a parametric link with the geometrical model. This parametric linkage ensures that any modification made to the geometry are also automatically reflected in the analysis. This dynamic adaptability underscores our commitment to the concept of a single source of truth. Changes in design no longer mean starting from scratch. Instead, the analysis evolves in tandem with the geometry, ensuring accuracy, saving time, and enhancing reliability across the project lifecycle. Furthermore, the user plays a crucial role in defining various parameters that are essential for a detailed and accurate analysis. This includes setting up the auto-numbering, specifying BIM units, and determining structure units that contribute to the structural integrity. Additionally, users can define load-only units, which are considered for their load effects, but not for their stiffness contributions, enhancing the precision of the analysis. The software also accommodates the challenges of auto-grillage setup, ensuring that the structural model accurately reflects the intended load distribution and support conditions. The pre-stressing of tendons, a critical component for certain designs, is carefully evaluated based on the geometrical model and predefined stressing actions, ensuring that the effects are accurately incorporated into the analysis. Positions of bearings, necessary for the distribution of forces and the overall behavior of the structure under load, are also defined by the user. This level of detail and user control ensures that the analysis not only adheres to the specific requirements of the project, but also leverages the geometrical model for a comprehensive understanding of the structure's behavior. Structural analysis within our system is designed to be a semi-automatic process, offering a blend of automated capabilities and user-driven customization, as we briefly touched upon in the previous slide. The initial model is directly derived from the geometrical definition, ensuring a seamless transition into the analysis phase. The subsequent step involves defining the construction sequence, which outlines how the bridge will be constructed. This critical phase is entirely under the user's control, allowing for the specification of one or more construction stages. Each stage encompasses various phases of constructions, such as pier construction, main girder erection, and the application of loads and design checks. This user-defined approach ensures that the analysis accurately reflects the intended construction methodology. Following the activation of the structure, the user then proceeds to define the loads. This encompasses everything from static loads, such as self-weight and superimposed dead loads, including settlement, wind, traffic, and earthquake loads. With all load scenarios established, the user then moves on to define superpositions and combinations, setting the stage for the execution of final design checks. This step culminates the structural analysis process, ensuring that the structure not only meets design requirements, but is also prepared for real-world conditions. After the construction schedule is established and all loads and phases are defined, our software steps in, adopting an open and interactive approach. It diligently analyzes the input data, proceeding to generate the necessary calculation tasks. These tasks are clearly displayed in the logging view, ensuring transparency and real-time feedback throughout the process. Tasks within the system can be generated in two ways: automatically, based on predefined settings, or manually, offering users the flexibility to tailor the analysis to specific project needs. This dual approach marries automation with user control, providing a balanced, open-ended system that adapts to the unique demands of each project. By offering this level of openness, combined with user-driven control, the software not only streamlines the analytical process, but also empowers users to steer the project analysis according to their precise requirements. This ensures that the final analysis is both comprehensive and customized to the project's specific conditions and objectives. The final stage of our structural analysis takes place within our design code engine, where we conduct comprehensive checks on concrete structures against two major standards. For this is one Eurocode, and on the other hand, it's ASHTO. For Eurocode, we've gone a step further by incorporating several national annexes, including those from Germany, France, Spain, and Austria, among others, to cater to a broader range of project requirements and local compliance needs. Our analysis covers a wide spectrum of checks. We assess linear stress and design the necessary reinforcement to address bending, shear, and torsion forces. Additionally, we evaluate the potential for brittle failure, crack formation, and fatigue to ensure the structure's long-term durability and safety. Detailing checks are also a crucial part of our process, ensuring that every aspect of the structure's design is scrutinized for compliance and practicality. Importantly, Our DCE is designed to be transparent and user-friendly. We provide an extensive report detailing all the calculations, including equations and the standards applied throughout the analysis. This ensures that the process is not a black box. Users have full visibility into the methodology and can review any aspect of the analysis at any time. This level of transparency is crucial for trust, verification, and ultimately the success of the project, ensuring that all stakeholders can be confident in the integrity and compliance of the structural design. After completing all necessary calculations and checks, the next step is to compile an extensive report that effectively presents the project's details and findings. To facilitate this crucial phase, our new reporting tool operates within the familiar environment of Microsoft Word, creating a seamless final step in the process. The integration between ALLPLAN Bridge and the reporting tool is achieved through a sophisticated data export function and a comprehensive intermediate database that houses all the numerical data. This setup ensures that every piece of information, from tables and images to detailed reports, maintains a parametric link to the source data. And this parametric linkage is key. It ensures that users are promptly notified of any changes in the data, providing them with the opportunity to update the report accordingly. This dynamic connection between the project data and the reporting tool not only streamlines the reporting process, but also guarantees that the final report is accurate and up-to-date as possible, reflecting the latest project details and analysis outcomes. Concluding, our ecosystem of advanced features is the automatic reinforcement generation, which exemplifies the seamless parametric link between bridge and engineering. After the bridge analysis is complete and the reinforcement data is defined, we leverage the power of Python scripting to generate parametric reinforcement models in ALLPLAN engineering. This process ensures that the reinforcement geometry perfectly aligns with the structural shape as defined in ALLPLAN Bridge, covering longitudinal, shear, and torsion reinforcement needs. Moreover, this system supports a bidirectional link, meaning any modification made to the reinforcement details by the detailer, for example, can be reflected back in the analysis. This dynamic interaction ensures that the analysis remains consistent with the project's evolving details, enhancing the accuracy of the design and the efficiency of the workflow. This bidirectional capability not only streamlines the design process, but also ensures that the final construction documents are accurate, reflecting the most current analysis data and detailing adjustments. Let's take a moment to reflect on the journey we've embarked upon today. We've explored a range of innovative features and methodologies designed to transform the way we approach infrastructure projects. As we conclude, I would like to highlight significant impacts of these advancements across three critical areas: time savings, quality of deliverables, and long-term value. Firstly, our focus on automation and efficiency is a game changer. By leveraging automated processes for structural analysis and reinforcement generation, we significantly cut down manual labor. The dynamic updates facilitated by parametric links ensure that changes are reflected instantly across all aspects of the project, from design through to reporting. This not only saves time, but also reduces the potential for errors, making our workflow more efficient. As we pivot from the tangible benefits of time savings, let's consider how these efficiencies translate into the quality of our project deliverables. The precision and accuracy we achieve through our advanced modeling and analysis techniques set a new standard in project outcomes. Our commitment to comprehensive analysis, adhering to international and national standards, ensures our deliverables meet the highest quality benchmarks. Furthermore, the enhanced collaboration facilitated by our bidirectional link system ensures that all stakeholders are always in sync, elevating the quality of our final deliverables. And while the immediate benefits are clear, it's essential to look beyond the horizon and understand the long-term value these innovations bring to our projects and practices. Our approach is built for the future. The adaptability of our tools and processes ensures we can meet evolving project requirements and standards, providing long-term relevance and value. The integrity of our data, maintained through a single source of truth, lays the foundation for reliable lifecycle management of infrastructure projects. Moreover, our continuous investment in innovation positions us at the forefront of technology, ensuring that we offer long-term value to all stakeholders involved in the project lifecycle. In conclusion, the methodologies and technologies we've explored today are key to transforming our approach to infrastructure projects, promising significant time savings, superior quality, and lasting value. As we move forward, embracing these innovations will be crucial in shaping our industry's future. Thank you for watching, and I encourage you to reach out with questions or to engage in further discussions on applying these strategies to your projects. Thank you.